I'm going to do an audience Rorschach test with you. So the question is, when you look at this, do you see a monster in the middle or two ravens talking to each other? Oh, wait a minute, wrong Rorschach test. That's the one I intended to show you. When you look at this map of Canada, are you looking at aftershocks of former large earthquakes, or are you looking at background seismicity? And obviously this kind of also involves psychology because it's very difficult to know. And for example, if we just zoom in on a spot there, if we would assume that these are background earthquakes, then this area has a higher hazard because it has a higher productivity of earthquakes. If instead we assume that this is the aftershock sequence of an event that occurred long ago, then at least for large shocks, it probably has a lower probability than the regions to either side of it, which would be higher. So the answer that you get depends very strongly on whether or not you can tell if these are background earthquakes or aftershocks. And the same is true if we look at Australia. So in Australia, although there are about a dozen active faults, they're short, they're disconnected, and most of them have only been active once in about 10 to 20,000 years. So by and large, the hazard that's depicted today for Australia is based on smoothing this rate of small earthquakes. And the question is that getting it exactly right or exactly backwards? And this is very difficult to know. Now, two possibilities are that the duration of an aftershock sequence would grow with its productivity, which is based principally on the main shock magnitude. Well, intraplate areas probably have smaller maximum magnitudes than plate boundary areas, so then you would expect aftershock sequences in a place like Australia or Canada would tend to be short. If instead the rate-state friction proposition is correct, or there is any kind of relationship between aftershock duration and how slowly a region is stressed, then a place like this would be expected to have long aftershock sequence, and the picture comes out differently. So let's go back to North America, and you can see that as the USGS depicts the hazard today, it's largely, but not exclusively, relatable to the concentration of seismicity. So this is one element that has been used in trying to represent hazard. And as you can see, as we've just heard in the last couple of talks, there are views on both sides of this story. But the question one needs to answer is, what promotes very long aftershock sequences, and are they common or not? Now, to do that, let's just take a look at what aftershock duration is. So we have an earthquake, and we have an Omori decay, and then we finally hit the background rate, and so that is the duration. Now, what about if we have the same K value, the same productivity, and the same Omori decay, do aftershocks all have the same duration? And the answer is no, they don't, because if we have a lower background rate, this second earthquake in blue has about 2 orders of magnitude longer duration. So apparently, background rate really matters. And so the issue here is to try to find some way of determining whether or not earthquakes are have long durations or not. And several approaches have been tried. The first is the one by Ebel, where he just looks to see if the size of the historic main shock is consistent with today's seismicity. You need to know about that main shock, and you need to know its size accurately, which is quite difficult. Seth Stein talked to us, I should say Seth, no relation Stein, talked to us about the trying to determine if recent seismicity is decaying. You can see above it's very difficult to decide, for example, if those Nevada earthquakes stopped decaying in 1980 or sometime well into the future. And Morgan has talked about other approaches that she and Ferdinand and Atkinson have taken to look at the decays. We're taking a different approach. What we're doing is measuring the background rate before the earthquake so we know it, and then measuring the Omori decay, and then projecting when that aftershock sequence should end. And so what matters here is how you measure aftershock duration. It's a measurement that turns out that it's easy to get wrong. So here's how things are working when everything is going well. You measure the aftershock zone and the background activity in the same area, and that area is only as large as aftershocks extend. If instead you measure both in a much larger area, you'll get many more background shocks where there aren't aftershocks occurring, and you will get an apparent duration that's way too short. So the strategy that Shinji Toda and I have taken is to measure in an area that corresponds to 0.1 bar static stress change, which tends to correspond to the limit of all-fault aftershocks. Now, we're conducting this experiment not in the United States, but in Japan. Two reasons why Japan is really the best place to do this. First, Japan is the place where the background rate can be best determined because of its magnificent catalogs. And the second is that we have one earthquake, the Tohoku earthquake, a magnitude 9, which triggered seismicity all over central Honshu, all within that 0.1 bar stress regime, that clearly shows strong increases. So we can decouple the problem of the Mainshocks magnitude from the aftershock duration. If aftershock duration is relatable to Mainshocks magnitude, all these red boxes should have the same durations. And so when we look at some of those boxes, you can see very strong turn-ons of seismicity at the time of the Tohoku earthquake, and you can see very different background rates, if lower left, Nikko versus Iwaki, for example, and we can easily measure those background rates. When we do so, and we measure the Omori decay, we get pictures like this, where the red line is the background rate. And you can see for this same main shock, magnitude 9, we have everything from about a 2-year aftershock decay to rates that project basically out to the end of the Holocene. And the Omori decay functions are rather similar to each other. So for one event, we seem to have an enormous range of at least projected aftershock durations. Now, we also looked at 8 magnitude 7 and larger earthquakes in Japan, largely on a transect across the trench. Here is what the cross-section of those regions look like. Some are in very active tectonic environments along the megathrust, and others, like the 2008, are in areas that are in the very slowly deforming areas. So the blue, red, and green earthquakes, I'm going to show you the aftershock durations on the next slide. So here's the red, and you can see that it hits the background in about 5 months. These are all I'm going to show you 3 earthquakes of all the same size. So here's another one, and this one has a duration of projected to be about 50 years, and same with this. So same size, very different aftershock productivities by about an order of magnitude, and very, very different durations. So quite a bit of variability. It's not related to magnitude. And when we regress all of the earthquakes that we have, here's the relationship. There's no dependence on aftershock duration on magnitude. Instead, it seems to have something to do with the stressing environment where the aftershocks have occurred. Ideally, if we wanted to test the rate and state prediction, we'd need to know the stressing rate on those faults. We don't. We do know, or at least approximately know, the fault slip rate, which is a proxy for stressing rate, and there we see a fair dependence. At least half of the variability is explained by fault slip rate. And so what this means is that, in fact, it's most likely that aftershock duration is a function of the stressing rate environment. And so going back to Canada, in an interplate setting like this one, that would suggest that many of these clusters of earthquakes are long-lived aftershocks. So how would we interpret that? If this was our view, how would we interpret that for probabilistic hazards? So we can go back to the example I showed you in the beginning. This is essentially a long strike-slip fault as understood by John Adams and the hazard modelers for Canada. And we can say, well, let's say this fault had a magnitude 6.5 or so rupture sometime, let's say, in the prehistoric period. Then we would expect that the probability of it re-rupturing is quite low. That's at 0 kilometers, because it's ruptured and it probably has recurrence intervals of thousands of years. But along either side of it, that's probably where the probability of the next rupture would be highest, if it triggered a neighboring rupture. Okay, so far so good. What about its aftershocks? Well, the smaller earthquakes, as we know from lots of experience, are going to tend to cluster around the region that ruptured. they're going to have the highest rate in the center of the rupture because they tend to come into the regions where the stress has been increased. So if you're out beyond the end of the rupture, let's say at kilometer 40, the rate of magnitude 5.5 earthquakes, the observable current seismicity, can be used to forecast the probability of larger events. But if we're in the center of this region, the 5.5s do not forecast the probability of big events because that event has ruptured sometime in the recent past. Now, how this plays out as b-values is probably something like this. The b-values are probably the same, but in the center of the rupture, the corner magnitude is lower, and outside, the corner magnitude is higher. This can also be represented in terms of a different b-value, which is what Seth was looking for in his presentation. But the b-value of 1 is basically what Morgan was finding in her presentation. So this experiment leads us to conclude that indeed, long aftershock sequences can masquerade as background earthquakes in intraplate regions. This is probably common, in which case we have to be careful about smoothing that seismicity and using it to forecast future hazard, because we may well inflate the hazard of large earthquake occurrence when we do so. Thank you. Yes, Werner.
I have one question. From your talk and also from Seth's talk, it seems that when you see aftershock, you are safer. And I wonder why you exclude the possibility to have large shock. I understand this cartoon, but what happened, for instance, in Magic Zone, you got 3 large shock. Just after the first Mainshocks, I could see some sort of aftershock decay. So I say, oh, this is aftershock, so I could be safe. But actually, you got 2 large shock. This happened in a few months, but it could happen also in a few decades, like probably happened in Omori. So I'm wondering, okay, I understand this cartoon, but probably it's too simplistic. I mean, what we see in reality is that also large earthquakes tend to cluster. And this happened during an aftershock sequence. So I'm wondering why you are giving so less emphasis to post-probability.
So Werner Marzocchi points out that the weakness of this analogy would be that New Madrid itself produced many large or several large earthquakes in a closely spaced physically in a short period of time. And I would say that the difference is this is a simple model for a single fault. New Madrid appears to be a cluster of faults, 4 or 5, in different close proximity to each other, in which case one event could trigger other events nearby. In other words, there are a lot of places where we see those peaks at plus or minus 10 kilometers. So if we have a complicated faulting situation, the April 2012 Indian Ocean earthquake is another example at the other end of the spectrum, and an 8.6 that occurred on many different faults in close configuration, then this is too simple. So we do always have that possibility of something large being triggered, but I would say that most of our evidence says that in general, the situation here where the small aftershocks are not forecasting the rate of large earthquakes is more typical. Do we have time?